so broken. Yep. That's very frustrating. So I'll have to use the built-in microphone. Not a problem. Just won't sound as good. But at least it'll sound like something. So today we're going to talk about the range equation. We are going to do a derivation. And you must understand that in this class on the AP exam, you will be required to do derivations. The word derive is a specific instruction on the AP Physics C exam, as distinct from determine. If you are given two questions and one says determine and one says derive, they are asking two different things, even if the rest of the problem sounds exactly the same. Determine means that you may present the least amount of information necessary to get to your answer. However, derive means you must show from a first principle a successful combination of expressions to reach your answer. There is a higher threshold of proof required for the word derive than there is from determine. So a determine could be just write down an answer, but derive will require you start from a first principle. They are different. Today's derivation is not something you would actually have to do on the AP exam, but it's in the spirit of what's expected on the AP exam. We're going to derive the range equation, because if I don't derive it with you guys, one of you is going to use it on a test because you will have read ahead in the textbook in chapter 3 and have seen that there is something called the range equation. It also shows up all over Khan Academy. So I know somebody knows all about the range equation because I keep hearing about it. Today we're going to talk about what the range equation is and its limits. It is not a magical panacea that will solve every single projectile problem. In fact, it probably solves the least amount of projectile problems. It is a special case of a small subset of problems. So if you're going to use the range equation, you better verify that delta y equals 0. It is the only time this can be used. This will only work when an object lands at the same height in which it was launched. It's the only time it works. But every year somebody uses it outside of those circumstances. Every year I emphasize that you can't use it then, but it doesn't seem to change the fact that people are determined. So we're going to derive the range equation. And the range equation is the result of eliminating time from this chart. Remember, solving a projectile problem has been about solving for time on one side and plugging it into the other. So we've had a vertical side and a horizontal side. And in each case, we know that there is a variety of information that is pertinent to each side. Now, generally, for the problems we've done recently, especially the ones where delta y equals 0, we've been dealing with the case where the object has been launched at some angle with some initial velocity. And that has resulted in a pretty straightforward projectile that travels up into the air, comes back down, landing at the same height in which it was launched. But under these circumstances, we have shown that you can use this chart to solve the problem by solving for the time and substituting it on the side of the equation that matters most. For most of these, it's been solving this side by having three pieces of information. Today, we will generate a new relationship that exists only under these circumstances, where delta y is equal to 0, by eliminating time on the two equations that you get for each side of this function. I.e., the left side, we have been using delta y equals 1/2 a t squared plus vy naught times t. And on the right side, we've been using delta x equals vx times t. So we're going to put these together and eliminate t. Does that make sense? Let's begin. Not a whole lot to do, actually, but we're going to do it anyways. We're going to start by saying that we know that under these circumstances, the initial y velocity is v naught sine theta. We talked about this the other day, that we can use a little bit of trig to break up our velocity into rectangular components. A horizontal component and a vertical component. V naught sine theta is the vertical component, the initial y velocity. Generally, I'm using the fact that the object is accelerated by the acceleration due to gravity as our acceleration. And last, that the horizontal velocity is based on the cosine of the angle. So nothing new here, right? This is what we've been talking about so far. So to start this problem out, I want to also make a reminder that these are vector quantities. It is clear, I hope to you, that the only way you can launch something off the ground is for it to be shot upwards into the air. There's no way we can have a negative velocity here. But if we say that upwards is positive, then we need to explicitly state that our gravity is going to be pulling it downwards. I am assigning direction. Now, there's no numbers here. I have expressions that represent the numbers that will be in this particular problem. This is our derivation. So that at the end, I will have a new expression that can be used in any circumstances where delta y is equal to 0. So there's no specific number here. Instead, what I'm going to do is create a function that has all the things in it I would associate if I were to have numbers. But instead of numbers, I will simply put in the placeholders, the v0 sine theta and the negative g. Now, we've done this a number of times, so there's nothing really different here. I'm not going to change what we've been doing. I'm going to factor out a t in this formula so that I can get a solution for t. First thing I'm going to do is, like I said, factor out one of the t's. So I just factored one of the t's out. Everybody okay with that? I'm going to set each of these equal to 0 to get an expression for t. The first one is obvious, t equals 0. We knew that that's a possible answer. We asked math to tell us when the object was on the ground, and it was on the ground at t equals 0. But the other one, 1/2 times negative g t plus v0 sine theta equals 0. That's also another expression for t. I want to get t by itself in this expression, but as you can all probably attest, it's way near the bottom of the screen. It's getting hard to see. So perhaps we can do that to kind of help us. I'm going to move this term to the other side of the equation. That makes it positive. Everybody good with that? I'm going to solve for t now by multiplying both sides by 2 and dividing both sides by g. So multiply by 2 and divide by g, giving me a new expression where t equals 2 v0 sine theta over g. Questions? Delta x equals vx times t. In place of delta x, I'm just going to write range. Somebody yesterday asked me, is this the same word that we associate with the word domain? For the domain and the range? No, it's not. We use the word range here to indicate a place, like downrange. I'm at a driving range, or the driver's ed range. It's a place. So in this case, the word range here just indicates a location. For us, this location is where the projectile lands. For Vx, I'm going to use what was written up in the chart, which is V0 cosine theta. But for t, I'm not going to put t anymore. I have an expression for t. So that's going to be 2 V0 sine theta divided by g. Now, there's not a whole lot I can do here, but this is a fraction. I'm going to put all the components of the fraction on the top. I'm going to bring forwards the coefficient, the number part, because we generally list a number first in an expression. I have two V naughts here. So V naught times V naught is going to be V naught squared. And I have a sine theta and a cosine theta all over G. This is the range equation. It's not particularly useful in this form, but at least you don't have to solve for time. If I told you that I launched something at 25 meters per second and an angle of 65 degrees, you could put 25 in here and 65 in here and in here, and you could bust it all out and figure out where it lands. However, the reason this actually has merit, the reason it has some use, is because there are things called trig identities. Raise your hand if you've heard the phrase trig identity before. So that's what I expect about half the group. Anybody who's completed pre-calculus will know all about trig identities. You'll learn to hate that phrase. They're not particularly interesting. It's substituting one trig function for another. Everybody in the room who's had some trig knows actually a couple trig identities. For example, it is probably known that, say, do you see it? Do you see why that might be useful? If not, pay attention. Over here, there was no way for me to separate out theta by itself because there was two trig functions here. So I couldn't get theta by its own, on its own to solve for the angle. But when I do this substitution, I get a function where I could solve for sine 2 theta, which means I could solve for theta on its own. The range equation is one of the only ways to find an angle that's required for a launch. It's one of the only ways. But we've done a whole lot of derivation here. We started at a basic principle, two motion equations, combined them together to get a new relationship called the range equation. Do not forget that all this is predicated on the idea that delta y equals 0. Use this in the wrong circumstance, and I will laugh at you, maybe publicly. So you must make sure that in the circumstance you use it, the object is launched and lands at the same height, or else you can't use this. And I bring it to you guys with a full derivation so you understand where it came from. It was just the result of eliminating time. Now, to understand why it's interesting, or at least moderately interesting, I'm going to tell you why. We already anticipated the direction of gravity here. By putting an explicit negative sign here, we have already said to the problem that we expect gravity to be acting downwards, so I don't have to blindly do it later. You'll notice that I am very intentional about when we use a negative sign. You've got 1 minute to figure out the answer to this question. If I launch something at 40 meters per second that I want to have travel 150 meters, what angle should I use? This can only be solved with the range equation. You'll notice I'm not drawing any chart. I've got the range, the launch velocity. Bless you. Those usually are worse than a sneeze, so.
My sneezes are really, really loud.
I am looking forward to a good solid sneeze. All right, so let's look at this. Yes, ma'am. I was hoping somebody would ask me that. Why is it not negative 10? Let's stop here, and let's make sure that everybody is caught up to me, because I have some important things to say that should make it into your notes. Did everybody get to this point? Multiplied both sides by 10, got 1,500. Divided both sides by 40 squared, which is 1,600. This fraction is important. It's the launch velocity and the launch range. It's range over velocity. If this fraction is greater than 1, you can't hit the target because there is no sign that can be greater than 1. So you didn't do anything wrong. There just isn't an angle that will hit that target. So this number has to be less than 1, or there is no answer. Next, and I think this is pretty important, you're going to get an answer for this. You're going to do 1,500 divided by 1,600. You're going to get, what, 0.9035? Oh, sorry. 90375? Fine. You're bumming my high. And generally, you're going to take the inverse sign of both sides. Be careful here. You guys who are in mathematics classes, you'll get your 70 degrees here and think that you're done. But you're not. Now, many of you think that I'm talking about dividing by 2. I'm not. I'm talking about the fact that for the most part, in this class and in all of the other classes, when you've taken the inverse sign, you've just assumed I meant I want the angle between 0 and 90. But sine in the first quadrant is positive. But sine in the second quadrant is also positive. Not everybody knows this in this room, but a lot of you do. Now, we would normally not care about the second quadrant because I'm thinking, if I'm standing over here and I'm trying to hit something over there, I don't really care about any angle where I would throw it this way. It doesn't seem to make any sense, except that I'm dividing by 2, which takes the angle that's over here and now places it back over there. The supplementary angle here is 110. That's what goes with 70, right? 70 plus 110 equals 180. Since I have to divide by 2, where is it? Down there. Since I have to divide by 2, that takes the supplemental angle and puts it back in the first quadrant, making it a possible answer, 35 degrees and 55 degrees. As I said to you yesterday, all of these have 2 possible angles. It's a consequence of the math, and the math has to bear it out. So although you will get one angle from the first quadrant, the second quadrant answer works. Now, I'm not asking you to change anything from yesterday. I'm going to say the things I said yesterday, that the first angle you get is correct, but the complementary angle also works. What I'm showing you guys is that for you guys who say you're good in math, math has to always work, or else we don't really call it math anymore. It has to be intentional. It's like throwing away the 1t, not recognizing that t equals 0 is an answer. Same way, the other angle exists because it has to be predicted by the same mathematics that tells us there's the first angle. So there are 2 angles. There's 70 degrees and there's 110. And when I divide them both by 2, it puts them both in the first quadrant and they make sense. And if you don't like any of that, the angle and its complement both work. Always. Now, the bell will ring in just a moment. But I need you to understand that you've done everything you need to solve the easy questions. But there's nothing more for me to teach you to solve the harder ones, except for time and experience. The only difference now is that now that you've done the two basic problems, one where there's no horizontal velocity and one where there's no displacement, you should be able to do the hard problems. The ones where there will be a delta y and an initial y velocity and an acceleration and a time. No longer does there have to be any zeros. I can launch something off of a height and have it land below me. And when I do, what that really means is that there's going to be a quadratic that has to be solved to get the 2 times. The real projectile motion problems are a little bit harder mathematically because I don't have a zero in there making them easy to solve. If I take the problem we just had and put it on top of a hill that's 20 meters tall, I launch it at 35 degrees and 40 meters per second. I'm going to have minus 20. I'm going to have 40 sine 35. I'm going to have negative 10. And that, my friends, requires the quadratic formula to solve. It's the only difference, but it's a lot. It makes these incredibly tedious. Really, really heavy in the mathematics side and not very heavy in the physics side. But this is the level you're expected to work at. Now, I will tell you, you could do it without actually having to solve a quadratic. You could find the final y velocity instead of finding the time. It saves you, because then you could use a different formula, maybe an easier one, to find the time. You could do this in 2 steps and not have to use the quadratic formula. But be careful, and write this in your notes, please. To get this answer, you will have to take the square root of both sides. You see that, right? Because to get Vy by itself, you'll have to take the square root because it's squared here. That means that you'll have square root and a bunch of stuff in here. Plus or minus have better be applied here. That's why there's 2 different times. There's the possibility the object's moving up and the possibility it's moving down. In the case of this one, which would you choose, the positive or the negative root? You would choose the negative root because it's very likely you would have chosen, or I already have chosen, that downwards is negative. So you don't have to do the quadratic if you don't want to, but you might. All right. A sine of theta is equal to cosine of the complement of theta, meaning sine of 30 degrees is equal to cosine of 60 degrees, because you're just switching which angle of the triangle you're looking at. And you might not have ever thought of it that way, but this is considered a trig identity. Now, there are books full of trig identities, and I don't mean that in a minor way. If you look up trig identities, you will find page after page after page of different formulations of trig functions. The first one all of you are very likely to learn about is that sine squared theta plus cosine squared theta equals 1. This is actually just the Pythagorean theorem. But you'll learn it. Again, you'll learn it in pre-calc. Lovely. And there are lots of other ones. Probably one that will serve us, that I will expect you to be able to use in class, is that sine over cosine is equal to tangent. And that one you should have actually already learned, but I am finding more and more that trig might have been glanced over a little bit due to those last couple of months in 2020, if you know what I'm talking about. So there's one we're going to use today, and everybody in here who's had pre-calc should already know it. It's this one. Everybody know these? The sine A plus B, the sine A minus B, the cosine of A plus B, and the cosine of A minus B. If you had pre-calc, you were supposed to learn it, but by the looks on those faces, it doesn't look like you did. Sine of A plus B is actually sine A cosine B plus sine B cosine A. Now, I know. Why would I bring this one up? Let me tell you why I'd bring this one up. Because sine of A plus B could be written as sine of A plus A. And sine of A plus A is sine A cosine A plus sine A cosine A. Every place there's a B, I put another A in for that. And if you look carefully, I hope you all see that this side is 2 sine A cosine A. This side is just sine of 2A. That's a pretty good substitution. You see,